Okay, we're going to continue our integration. And we're doing example G here. Um, when I look at this one, the first thing I notice is that I don't have the derivative of the denominator present. So I might think about some of the more unusual ways of integrating that we have seen. And so if you consider this, this is the sum of perfect squares. We'll go back, let me arrow back a ways, and look at those trig identities, in particular the inverse trig identities, and notice how they have either a sum or difference of square terms. This one has a u on the outside of a radical. This one has just the radical. This one doesn't have a radical at all. But the point is when you see that sum or difference of squares, whether it's just out here alone or perhaps beneath a radical, then you might want to consider whether or not one of our inverse trig functions will fit. And actually, this last one, the integral of du over a squared plus u squared equals 1 over a arctangent u over a plus c, that's going to fit. Okay, so let's see if we can make that work. Okay, so how does that fit for us? Okay, well, I can think of this as a perfect square. Because this is the integral of dx over the square root of 5 squared plus 2x squared. Okay, so according to that pattern that we saw, this could be my a squared and this would be my u squared. Okay, we still have to do u substitution to make sure that we have the derivative present. Okay, but what I'm thinking is going to work for us right now is we saw, I'll write it here so we're all together, the integral of du over a squared plus u squared is going to equal 1 over a times tangent inverse of u over a. Okay, so we see we've got an a squared. That's going to be the square root of 5 squared. We have a u. That's going to be 2x. But what we need to make sure of is that we have a du. So if we say u is equal to 2x, then it follows that du is equal to 2 dx. And so for dx, we're going to substitute in du over 2. All right, so that gives us 1/2 times the integral of du over, we've got an a squared plus u squared. Okay, and according to the rule, we know that this integrates as, we still got the 1/2 that's going to just follow along. But then we're going to have 1 over a, so that's 1 over the square root of 5, okay, times tangent inverse of u. Our u is 2x over a, square root 5. All right, so we end up with 1 over 2 root 5 times tangent inverse of 2x over root 5 plus c. Okay, so let's look at h, which is similar. Well, you might not think, well, it is similar because in that denominator, we already have a difference of squares. One is a perfect square. And really, we can make any number a perfect square. Well, that's not quite the right term, but we can make it a square by taking the square root of it, right? That's what we did with 5. But here we got 1 minus x squared, all right? So we might consider some of the patterns. And for us, interestingly, we have sine inverse as a part of this thing. Okay, so let's just kind of remind ourselves, I'm going to go back again, of what the derivative of sine inverse is. Okay, and so we're going to get, for the derivative of sine inverse, it's going to be 1 over the square root of a squared minus u squared. Okay, and so let's consider our acronym LIATE. Okay, which means we give second priority for assigning u to inverse functions. So let's let u equal sine inverse of x. All right, then we just saw the derivative of that is 1 over the square root of 1 minus x squared dx. Okay, and that's exactly what we have. So if we rewrite this in terms of u, we've got the integral of u du. And of course, we know that comes out to be u squared over 2 plus c. Or if we write that in terms of x, then it's going to be sine inverse of x squared over 2 plus c. All right, let's keep going forward. All right, now we've got some definite integration. And in this one, again, we're still just, using u substitution. When I look at this, I'm going to try to determine if one expression is the derivative of the other, or maybe a multiple of the derivative. Okay, if it's a multiple, then we can always multiply or divide to make it work. All right, and then remember, I think in both classes we've talked about if you got sine and cosine, how do you decide which one you want to let u be? Well, we're going to let it be the denominator in this case. If you have it in the denominator, then choose that for u and see if that works first. All right, so I'm going to say u is equal to x plus cosine x. And it follows then that du is equal to 1 minus sine x dx, which is exactly what we have, right? We can rewrite this now as the integral, and we need to change our limits. We'll come back to that in just a second. But we've got du over u. Okay, and we already know that that's going to be, well, hopefully we know that's going to be natural log. Okay, as far as the limits go, we get u equals 0 plus cosine of 0. Well, cosine of 0 is 1, so our lower limit is going to be 1. All right, and then if we put in pi over 2, cosine of pi over 2 is 0, and so the upper limit is going to be pi over 2. All right, you want to check, if you're not sure, make sure that the upper limit is larger than our lower limit. Okay, and when we do that, we get natural log of the absolute value of u. But of course, we can already see that both of these numbers are positive, so we don't have to worry about that. So it's going to be natural log of pi over 2 minus natural log of 1. Well, natural log of 1 is 0, so our final answer is just natural log of pi over 2. All right, in B, we've got the integral from 1 to 3 of e to the 2 minus x dx. Okay, this one's pretty straightforward. Again, using Lie8, algebraic comes before exponential. So let's try u equals 2 minus x. Okay, that's our algebraic expression. And so it follows that du is just going to be negative 1 dx. All right, so we got dx. We just need to make it positive. So negative du equals positive dx. Oops. And so we get that this is equal to the integral of e to the u du. If we put the negative on the outside of our integral, all right, we can look at changing our limits. All right, if I plug in a 1, then my new lower limit is going to be 1. And if I plug in 3, my new lower limit is going to be negative 1. Okay, so because we've got the lower number on top, we got to flip this. And that's going to cause the whole thing to be negated. So we get the integral, positive integral, from negative 1 to positive 1 of e to the u du. And of course, we know that that's e to the u. We're going to evaluate it from minus 1 to 1. And so we get e to the 1, okay, minus e to the negative 1, which is 1 over e. All right, and so our final answer is e minus 1 over e. All right, what about C? And please feel free to pause the video and work these on your own and then come back and check. But we've got the integral from 1 to 3 of e to the 3 over x squared. So we have a lot of things going on here. But one thing we know about e raised to a power, if we're going to be able to integrate it, we've got to have the derivative of this power present, right? It needs to be there. So I'm thinking that we'll try u equals 3 over x first. All right, then it follows that du is going to be, well, first of all, let's rewrite u as 3 times x to the negative 1. So du is minus 3 times x to the negative 2 dx. Okay, or another way to write that is 3 over x squared dx. Okay, I'll say negative 3 over x squared dx is equal to du. Well, we need 1 over x squared dx. So I'm going to divide both sides by negative 3. So du over negative 3 equals 1 over x squared dx. All right, so this becomes the integral. Well, negative 1/3 times the integral of e to the u du. And of course, we know the integral of e to the u is e to the u, so we get minus 1/3 times e to the u, okay? And we've got to evaluate this using our new limits of integration. So if we plug into our expression for u, when I plug in 1, I get 3. So that's my new lower limit. And when I plug in 3, I get 1. That's the new upper limit, all right? So that said, we really need to flip all of this around. So we get positive 1/3. And I can go ahead and write, well, we're still doing e to the u from 1 to 3. Okay, so we get 1/3 e cubed minus 1/3 e. All right, and there are lots of different ways we can factor off the 1/3. We can even factor off an e is still going to be there. But I think we know how to write this in lots of different algebraic ways to express our answer.